Okay, so here's where we left off, right? We were dealing with this trig function. I redid the table so it's a little bit neater, right? So we said, remember that the domain would be all real numbers except we have to exclude the integer multiples of pi, right? Well, let's just focus on only the we're going to have an infinite number of those vertical asymptotes, right? The places where the function's undefined. Negative pi, 0, pi, 2 pi, 3 pi, etc. But let's just focus on the values between 0 and 2 pi, because we're going to get a repetitive cyclic behavior here with our cotangent function, right? Everybody agree? We're going to get the same kinds of things. We're going to get this, we're going to just repetitions of the same critical numbers, and the same zeros of the second derivative. All those things are going to cycle again and again and again, right? It's because we're just taking laps around the unit circle essentially. Okay, so let's look at our first derivative stuff, right? We said that if we differentiate, we got 2 minus cosecant squared x. We decided that that was equal to 0 wherever cosecant squared x equaled 2, and we came to the conclusion that that was going to be these 4 places on the unit circle, on any lap of the unit circle, right? It could, but I'm going to have an infinite number of laps, but we'll just consider the one lap between 0 and 2 pi, okay? So there, and there. And those are the angles, pi fourths, 3/4 pi, 5/4 pi, and 7/4 pi. So we added those values. Those are the yellow critical numbers, right? And so let's fill in some blanks here. Hopefully my pen's working well enough to do this. I don't know what's going on with it, but these are places where our function is undefined. And so we recognize those as vertical asymptotes. These were zeros of our first derivative. Pi fourths, 3/4 pi, 5/4 pi, 7/4 pi, and we'd keep going, but we're just taking our first lap of the unit circle. So those are places where we know we have horizontal tangents because I have 0 first derivatives. Okay, what about the second derivative? Let's go back and look at our second derivative. So the second derivative, would everybody agree if I differentiate 2, it goes to 0, right? And if I differentiate negative cosecant squared x, that's a chain rule issue, right? So are we, just type it in chat for me, are we in this function cosecant squared, what's the outermost part of that composition? Is it a squared function first or is it a cosecant function first, looking from the outside in? In other words, do we have to differentiate power rule first or cosecant first? Okay, good. It's the squared, isn't it? Yeah, so we have hand squared to begin with. So we're going to get negative 2 times hand, which is cosecant x to the 1. And now we got to look inside the cosecant, right? Or look inside the squared function. Inside the squared is a cosecant. What's the derivative of cosecant? Assuming you guys remember, that's negative cosecant cotangent, right? And so if we simplify that a little bit more, if I distribute or actually if I just multiply that out, negative times negative is positive, so I get a 2. I've got a cosecant squared times a cotangent, which is the same thing. If I want to write this in terms of cosines and sines, which is a good idea, then the cosecant gives me a sine squared on the bottom, the cosecant squared. Cotangent gives me a cosine on the top and another sine on the bottom. So I end up with 2 cosine x divided by sine cubed x. Okay? Okay. So then where is this equal to 0? Well, the second derivative is equal to 0 when the numerator is 0, right? So the second derivative is 0 when cosine x is 0. And where does that happen on the unit circle? Where is cosine x equal to 0? For what values of the angle x? Type it in chat. Here's my unit circle. Remember, cosine is the x coordinate, right? So where's that going to be? Okay, so yeah, so we're going to get when x is equal to either pi halves would be one place, right? So there's one place up there at pi halves. I could go around to 3 halves pi. I could go around again. Second lap, that would be 5 halves pi. And then 7 halves pi. And then when I start my third lap, that would be 11 halves. See what I'm saying? We just keep going. Or I could go backwards. I could start at 0 and go negative pi halves, negative 3 halves pi, negative 5 halves pi. How would I describe those then? Those are just a bunch of multiples of pi halves. How would I describe those multiples of pi halves? 1 halves pi, 3 halves pi, 5 halves pi, 7 halves pi. There we go. Okay, divided by 2 though, and Johann would have it, right? So it's going to be, they're odd multiples of pi halves, right? So it's going to be, an odd number would be 2n minus 1 times pi halves, times pi over 2. Okay, so in our first lap, that would just be pi halves and 3 halves pi. So in lap number 1, we'll just add those two values that correspond to zeros of my second derivative. So those are potential inflection points then, right? And we'll find out. Okay, so what about places where our derivatives, we found all the places where the first derivative was equal to 0. Are there any critical numbers where our first derivative is undefined? So here's our first derivative, right? 2 minus cosecant squared x. Well, cosecant squared x is the same as 1 over sine squared x. So the sign on the bottom is going to be equal to 0 at, these points on the unit circle. But what's the problem with that? Why are those not critical numbers? Why are the places where our first derivative is undefined, why are those not critical numbers? Maybe it's easier to just turn a mic on. We have such a small number here. Somebody click a mic on and tell me, how come those are not critical numbers? The zeros of the first derivative would just be 0, pi, 2 pi, right? It's all the places where the unit circle intersects the x-axis.
Is it because there wouldn't be like maxima or minima because there'd be like a sharp corner or cusp or whatever?
Well, in order for them to be critical numbers, they have to be in the domain of the function, are they?
No.
Right, they're not, are they? Right, those are the places where our function is undefined. And so because our function's undefined there, they cannot be critical numbers. And notice I get the same thing for the second derivative. Our second derivative, we've got signs in the denominators again. And so the zeros of the denominators are going to be the same as the places, we had signs in the denominators in our original function, and that's why we had to exclude all the integer multiples of pi. So that's where we have vertical asymptotes. So our table, we have all the important numbers there. Now we just have to finish the table. So how are we going to deal with our first derivative critical numbers? Are we going to want to use the first derivative test or the second derivative test here? Just type in a 1 or a 2. 1 for first derivative test, 2 for second derivative test. Definitely 2. Good. Definitely 2, right? We want to use the second derivative test. Get taken care of? Awesome. Thanks, Amber. So we want to use the second derivative test here because we've got the second derivative calculated, and the second derivative exists and is not 0 at each of our first derivative critical numbers, right? So all we have to do is evaluate our second derivative at all of the odd multiples of pi fourths, right? And we're just going to do that in our first lap of the unit circle, but this would extend forever for all infinite laps of the unit circle. This is going to be, because you weren't here this morning, this is going to be, it's going to, that I would just do that, yeah. And I'm taping both of these and they'll be up after school. So let's try that then. Our second derivative, here's our second derivative function conveniently written in terms of cosines and sines. So 2 cosine x over sine cubed x. Gosh, this darn pen. Or sine cubed x. Okay, so what about at pi fourths? What's that going to give us? Well, pi fourths, that's in quadrant 1, right? So both cosine and sine are positive in quadrant 1. So I'm going to get positive divided by positive is positive. So then this is a minimum, isn't it? Because we have concave up and a horizontal tangent. Okay. What about at 3/4 pi? So that's in quadrant 2. Think quadrant 2. In quadrant 2, cosine is positive or negative. Type P or N. In quadrant 2, okay, sine is, okay, good. Good. So we're going to get positive over negative cubed is negative. Negative. Okay, 5/4 pi is quadrant 3. They're both negative in quadrant 3, right? So I'm going to get negative divided by negative cubed is negative for an overall sign of positive. So there we go. And then at 7/4 pi, quadrant 4, that's where cosine's positive, sine is negative, right? And so finally, positive over, I got this one backwards, didn't I? That should have been negative over positive. Got the same result, but I want to make sure I get it right in my notes. Right, I would have had negative over positive, and this one's positive over negative. So we're negative. Okay? And look what we did in the process. Killed two birds with one stone, because now we also found we used these as test points surrounding our zeros of the second derivative. So these turn out to be points of inflection, don't they? Right? Because they're places where our second derivative transitions in sign. So there we go. Okay? And if we graph this thing, let's just graph it on Desmos and just show that this matches our graph. Okay, and let's, we can see that this thing is going to have, it's going to be repetitive. Now, each time the shape of the curve is going to be shifted vertically because we've got that 2x term in there. And this problem really would have been, this really, like on an AP test or something, it would have definitely said between 0 and 2 pi. Because so we'll just assume that it did. We'll just assume we're only looking between 0 and 2 pi. So on Desmos, I'll show you a little cool, if I can remember how to do this. There's a cool way to do this on Desmos. If you go into graph settings, you can just go from 0 to 2 pi. Oops. 2 pi. And let's go in steps of, how about pi halves? And on y, we'll just go as far as we need to get this thing to show up. So let's see, how about, we'll just try something like negative 50 to positive 50 and see if that looks good. That's not bad, right? We'll see we've got a minimum at pi fourths. We've got a maximum at 3/4 pi. We've got minimum at 5/4 pi, maximum at 7/4 pi. I probably didn't need to extend that so far. How about if I make this thing go from, we'll just go 15. Negative 15 to positive 15. That's a little bit easier to see maybe. Okay, and notice I've got vertical asymptotes at 0, pi, and 2 pi. Okay, and if I wanted to make my sketch look more like this graph, and let me get a picture of this graph, how about? There's my picture. All I'd have to do on my table is go in and plug in those values, right? I could evaluate my function at pi fourths, pi halves, 3/4 pi, and I could get ordered pairs that would be easier to graph on the XY plane. They'd give me an idea of where those points actually sit. We don't really want to take the time to do that right now, but we can see that if we do that, that's the picture we're going to end up with, isn't it? And we'd probably want to maybe draw in our vertical asymptotes. Okay, there it is. All right, questions? Everybody good on that? Give me 1 to 5. $3.7. That's pretty specific. I like it. Okay, that's a tough one. I mean, the trig ones are tougher. It would have made it a little bit easier if I had said in the original problem, whoops, if I had said on the, and I'm going to add this right now. If I had said that, it would have made the problem quite a bit easier. We wouldn't have had to worry about all those infinite odd multiples of, things like that, right? We could have just picked the specific values in our table, between 0 and 2 pi, right? That would have made things a little simpler. Okay. All right. I'm going to let you go. I think that's good for today. We'll start our new stuff tomorrow. Remember to be working away on the test. How many people is anybody done with the test? I think they're due. No. Okay. Not. Okay. So is like a week from Wednesday, is that going to be sufficient for you guys to finish all those up? Okay. Okay. So we'll say that. I think the deadline was something like that anyway, but if I need to extend it, what is the deadline here on that test? Let's look. And I might have said plural test. It's only one test, right? So it's curve sketching, 4/7. What day is that? That's next Wednesday. Good. So next Wednesday at 11 p.m. All right. If that works for everybody. Yeah, it's the 7th. That's it. Yep. Okay, good enough. You can hang her up for today. Good job. I'll see you on Wednesday.